All right, welcome everyone. Those of you who are online, if you would please go on Canvas to the week 12 module and go to the practice with the method of distribution functions. And folks in person, if you would find a spot at the board.
We can switch if you want. I'll go to take it.
All right, so once you have identified a color of pen for the Google Doc or a working marker for the whiteboard, let's do this problem. In a certain city, the future lifespan of retirees is a random variable x with an exponential distribution with mean 10 years. A whole life insurance policy offers a payout of 5x in thousands of dollars. We want to find the density function of the payout amount. So remember that the first step is to identify the range of possible values of our new random variable. So if you call that u equals 5x or y equals 5x, what's the range of possible values of that? And then write the distribution function, big F, of u or y in terms of x and little u or little y. Good, yeah, so we want to start by writing this just as a probability. So we're not yet using the density function of x. to double check the upper bound on your integral? If you want to be computing the probability that you wrote in step 2.
Wow.
That's right.
Well, then I'm confused.
All right. Can you narrow in on what you're confused about to help me help you?
Oh, I keep trying to integrate you. I think that's what's going wrong. My confusion is, yeah. Because I'm like, look, U is 0 to infinity. So I thought X was U in this situation. But it's not.
No. So now that you've written the probability in terms of the random variable x,
Yep.
now you can solve it as an integral with dx, just like we did back in chapter 4. So you do want this integral to be in terms of x. Your answer will have a u in it. So, Niall, your first way that you wrote the integral was correct.
Here.
Yep, you want it to be e to the negative x over x.
We were using some sort of like fundamental theorem of calculus because we had some variable up here, and then we were like putting it in the integral and changing the variables.
So you can do this in 2 ways. In this case, the integral is reasonable to do, so you can just integrate it and then take the derivative.
Okay.
If you wanted to try to use the fundamental theorem of calculus to sort of combine the integration and derivative into one step, you can.
Mhm.
But I would say maybe don't do that yet because you don't need to for this integral.
And you said we're going to have a u in our answer anyway, so it's okay that we have some variable in that upper bound for the integral.
Correct. Yep. Because our final answer is going to be a distribution function for u.
Yeah.
So it should be a function of u unless u is a uniform distribution. Nice, it looks good. Yeah, looks good, Matt. Looks good, Joe. I think your constant got messed up somewhere.
I'm sure that integrate probability. I'm never good with those types of integrations.
So it's going to be a small u substitution.
Yeah. The du is equal to just
Okay.
dx.
Negative 1 times the
Negative one
negative
times
x in there.
Then dx is equal to 10 du. So we're actually getting 110 times e to the u, and dx of 10 u. Let's just cancel that. Yep.
Should your E be negative?
Yeah, this is a negative outline. From this part right here. Right.
Here's the negative sign through. That looks better.
There we go. Took me long.
Cool. And then what's the final step in finding the density function?
Not quite sure.
So you found the distribution function, big F.
Yeah.
To
Take a
find
derivative.
little f, you take the derivative.
Yeah. So this is f of u.
All right. So then what is the name of the distribution of this payout amount? What's the derivative of 1 now?
I'm just not.
Yeah. So what we have here is an exponential distribution with a mean of 50. Nice job. Are there any questions about this one? All right. So our next problem gives us a bit of a callback to an activity we did in class a few weeks ago in the practice with continuous random variables activity. So I gave you a piece of R code that could simulate from the density function a times y to the b for y between 0 and k. So in this problem, we're going to use that idea and sort of understand how that code worked, how it did what it did, by simulating values from the density function f of y equals y to the third for y between 0 and square root of 2. So let's start with a random variable x that's uniform on the interval from 0 to 1. So the question is to prove that if y is equal to the square root of 2 times x to the 1/4, then y has the density function that we're trying to simulate from. So Kyle's starting out with a graph, good choice. Random variables are switched, yeah. Because the idea is that you start by writing the probability that y is less than or equal to y as the probability that square root of 2 x to the 1/4
So that equals
is less than or
big,
equal to 1.
that square root, this is equal to big y.
Correct. Yep.
That's what we're wrong. I thought it was little y, because it's y.
No, because we're always defining one random variable in terms of the other, so it's always a relationship between the capital letters.
Oh, yeah, because, yeah, okay, so we should put that, then that's, yep.
Yeah. You want that to be dx, because you want to integrate in terms of the variable whose distribution function you know. And why is it just dx?
Because it's just uniform from 1 to 0.
Yes.
And it just
Sort of the,
it's 1 over 1 is 0.
exactly. Good. And what's the range of possible values of y? Yeah, that should be a little left of y, not x.
Oh.
All right, nice. So now we can look at how we can use this. Is we can simulate random numbers from a uniform distribution on 0 to 1. Folks who are here in person, do you happen to have your laptops with you? I forgot to ask you to do that. All right, if you have your laptop with you, why don't you go ahead and give this a try? Tal, you're the only one without a laptop, so you want to try it up here?
There's no keyboard.
Oh, it's underneath the desk.
Oh. What trying?
What you looking for?
What am I trying with problem?
You are, well, you can click back to the Google Doc. So start by simulating 10,000 random numbers from a uniform distribution between 0 and 1. Call that x. And then we'll compute y by taking square root of 2 times x to the 1/4.
What are you trying to do?
So start by simulating x as a vector of 10,000 random numbers that are uniform between 0 and 1, and then generate y as a function of x. So Kyle, I saw you working on this using a for loop.
Yeah.
You can use a for loop for this, but you actually don't need a for loop for it. If you instead just do x equals runif parentheses 10,000, comma 0, comma 1, then it'll generate 10,000 copies of the random numbers in one go rather than having to loop through it.
Yeah, I just didn't know if that stored properly. So just one at a time. Can 10,000 like that?
Yeah, the default is from 0 to 1, or if you wanted to be explicit about it, you could do comma 0, comma 1 to specify what the min and max are.
Open mark villages too. Oops. What did this give me?
Yeah. And then, for example, you can make a histogram of y.
How do I run this?
It ran.
What?
But it's not displaying the values of y because you haven't typed y in the entry yet.
Oh yeah, that's definitely, yep.
I might need to scroll down.
Ooh. This is histo, right?
Yep. Yes.
I definitely don't remember all the.
Yeah, it's just his parentheses y.
Alright, that'll work. I don't know if I need to make it like light blue or something.
I usually enjoy making it light blue because I think that makes it easier to see, but this works fine. All right, so what do we see in that graph? How do we know whether we got it right? Sam?
It looks exponentially.
Well, hopefully it doesn't look exponential, but hopefully it looks like the graph of y to the third, or y equals x to the third, rather.
Right.
Because the shape of the tops of the bars of the histogram should represent the density function. So this is actually how many computer programs generate random numbers according to different distributions. Is someone will write a code to generate uniform random numbers between 0 and 1, and then they use this process to convert those into other distributions that the program might need. Kyle, would you switch back to the Google Doc and scroll down to the next problem for us?
Yeah.
So try using sum to find the empirical probability that y is less than 1.2. So Kyle, looks like you're working on it as if it's a part of a for loop.
Yeah,
Um,
I know.
you could make that work, but I think there's a faster way,
Hmm.
which is to put the check if y is less than 1.2 inside the parentheses of the sum. So you're actually going to want to close the curly bracket. Yep, close curly bracket and then press enter. So you get back to a caret, so it's ready for a new command.
Okay, iStudio.
Yeah, I still haven't gotten around to emailing the help desk to get them to put RStudio on this computer.
All right. So what's the check command?
So sum parentheses y less than 1.2 close parentheses.
Oh, shoot. So just like that will do it.
No, get rid of the close parenthesis right after the y.
Oh, gotcha.
And then you don't need the initial parenthesis at the very beginning of the line.
At the very end.
Very beginning,
Oh.
before the start of the sum.
Okay.
So what that's doing is for every entry in y,
Oh.
it's checking whether it's less than 1.2.
Yeah.
So that'll be a vector of 10,000 trues and falses. And then by taking the sum, we're treating all the trues as ones and adding them together.
Oh,
You can
very
use
good.
arrow up to repeat the previous command. Cool.
Woo.
So how you got empirical probability of 0.5159. Sam, did you get an empirical probability?
Yeah. 5173.
5173, so pretty close. All right. And then, Niall, looks like you've been working on the theoretical probability. Tell us about what you did.
Well, we're looking for the probability that y is less than 1.2, and we can see from the definition here that f of y is equal to that. This is the derivative part, so we have that f of y is just equal to y to the power of 4 divided by 4. So you can just plug in 1.2 to find the probability that that y is less than 1.2.
Nice, and that ends up being close to the empirical probability. All right. So now let's try part D. So we want to find the empirical value of the expected value of y, and then write the theoretical expected value of y as an integral in two different ways.
Empirically, we just is that the empirical probability?
That's the empirical expected value. Yep,
Okay.
looks good.
Now I gotta find the theoretical as integral. Two different ways, okay. What screen should I leave open?
Oh, we'll just put it on the Google Doc.
Oh.
Good, now you got one integral.
Yeah.
Yeah, so to get the other integral, the other way to find the expected value of y, think back to how you would have done this back in chapter 4. Back when all you knew was continuous random variables, finding their expected values, finding the expected value of a function g of x of a random variable. One to the 5 fourths?
I guess to multiply by a factor of x to get the expected value like we did up here.
Nope, it's just the integral of whatever you want the expected value of times the density function of the variable that you're integrating with respect to.
Oh, okay. So that's why it's just stays in the 1/4 thing.
Yeah. Yeah, looks good. And then, oh, you got the other way. Looks good.
did not do two integrals. I'm like, I'll make this expected value of f of integral.
All right, yeah, so we have two ways of writing this integral. One is in terms of y, we would take the integral of y times the density function of y. Joe, you would actually want y times y to the third here. Yeah. Dy, and then your endpoints would be the bounds for y, so 0 and square root of 2. The other way is to do it in terms of x. So thinking about y as being a function of x and using techniques from chapter 4. So we'd have the integral of the thing whose expected value we want, so square root of 2 times x to the 1/4, times the density function for x, which was just 1 on the interval from 0 to 1. So that's telling us that these two integrals should give us the same answer. Questions about that?
How do we get the range of 0 to 1 again?
The range of 0 to 1 came from what we were told about x at the beginning of the problem, that x was uniform on the interval from 0 to 1.
Oh, okay, thank you.
You're welcome. All right, so let's get started on problem 3 here. So two insurance clients experience hospital bills in the amounts of X and Y, measured in thousands of dollars, which are independent and uniformly distributed between 5 and 10. And each client has a health insurance deductible of 1. So what that means is that the client pays for any expenses up to 1, and then the insurance company pays for expenses beyond that. So if their expenses were 0.8, then the client would pay 0.8 and the insurance company would pay nothing. If the expenses were 2.3, then the client would pay 1 and the insurance company would pay 1.3. But here, X and Y are always between 5 and 10. So for sure, the client is paying 1 and the hospital is paying somewhere between 4 and 9. So our question is, write a formula for U, the total amount that the insurance company pays when you combine both clients' hospital bills. Sam, remember that the clients have a deductible of 1 each. That looks good. All right. Yeah, so we get that U is X plus Y minus 2, because the insurance company isn't paying the deductible amount. And then the joint density function, little f of X comma Y. What's that going to be? Kyle has 1/25. Looks good. How'd you get that?
I found the density function of X and f of Y, just multiplied them together.
How do you know you can multiply the density functions?
Because you said they're independent.
Yeah, it said they were independent. All right. And then what are the possible values of U? Looks good, looks good. So if the insurance company pays for everything except one for each of the clients, and each of the clients' amounts is between 5 and 10, the insurance company is paying between 4 and 9 for each person. So that means the total they must be paying is between 8 and 18. So that's going to give us our range of possible values on which the density function is going to be non-zero. So now, go ahead and write the distribution function in the form probability of y being less than or equal to something involving little u. Good. So we have the probability that x plus y is less than or equal to, or x plus y plus 2 is less, or x plus y minus 2 is less than or equal to little u. So then you can solve that for y on one side of the inequality and get probability that y is less than or equal to little u plus 2 minus x. All right. So in order to evaluate this probability, we're taking an integral over a region where x and y are between 5 and 10. And when u is greater than 13, that sketch looks like this. We're integrating over this gray region. Find the equation of this black line in terms of little u. So use what you wrote inside the probability there up above. And remember that what we're doing in this gray region is we're defining the region where x and y satisfy that inequality. The region whose probability we're finding. So you might be overthinking this. We want to shade in the region where it's true that y is less than or equal to u plus 2 minus x. So this line is the line y equals u plus 2 minus x. So that way, the region we're integrating over, all of the shaded region, are the combinations of x and y that satisfy y being less than or equal to u plus 2 minus x. And the reason why this is important is being able to find the equation of this line is useful for setting up our bounds of integration when we go to integrate over this region. Questions about this? All right, so we're out of time, so we'll leave this one there. But we'll leave this up here on the Google Doc as an extra practice problem if you'd like. And the key will become available on Monday at 5 o'clock. Thank you all for your attention, and I will see you next week for the method of transformations.
Thank you, Doctor.